Hi guys, I'm Nick from Metronome and this is Amal from Facebook, and we're just going to be talking about the work we've been doing to improve disaggregation using Datacenter TCP. So this is really going to combine congestion control, Linux kernel networking, and networking hardware in the form of MES 2.0 SmartNICs and also white box switches. So we're kind of pulling all these things together and we're trying to mesh it all and make something that'll work to increase the data center's efficiency. So to kick off with, what is disaggregation? So just to start very, very simple, this is really concentrating resources which are to be shared between a bunch of users. And in our case, the resources is the flash and the users are all the compute nodes. So this really provides us with a way of increasing our efficiency. That's why we disaggregate. So there was some work done a couple of years ago by the capacity team at Facebook and the guys at Stanford University, which defined this as being about a 40% improvement in utilization for flash storage. And there's a couple of papers on that. I've referenced one of them there at the bottom. So this is great, obviously, for a sort of standard server model, and that's what they were focusing on in this case. In this case, that would be equate to the Leopard or the Tioga Pass type OCP server. But we wanted to take this one step further. So what we were then focusing on was using this and applying it to the Yosemite V2 system. So the Yosemite V2 system is important for a couple of reasons, but the main one is that it's incredibly power efficient. So you're improving your compute per watt. So that's fantastic, but the problem we have right now is that latency-sensitive workloads are difficult to deploy on these systems. The reason for that is because of the fact that we have a incast problem. So if you look here at the 50 gig Ethernet compared to the 12 to 24 gig PCIe link to each one of these hosts, that means that you can actually, if you have bursty traffic patterns, like disaggregated flash storage, you end up in a situation whereby you're actually going to potentially have more traffic coming into the NIC than it can actually sync. Now, what happens when that happens? First, usually a NIC buffers for a little bit, but then it starts dropping packets. And as soon as you start dropping packets, you end up in a situation whereby you're going to have increased tail latency. And that's really why it's difficult to use for those purposes. So that's the problem statement that we were looking to solve. So what do we need to be able to solve this problem? We need a method to detect congestion, we need a feedback mechanism, and we need to be able to buffer and control the situation until our feedback loop is actually enabled. So those are the three things we need. To be able to detect congestion, that's what we're doing in the programmable NIC. We have very simple ways of writing some software which can sit on there and actually detect when the PCIe link is getting more congested. The second thing is we need a feedback mechanism. That's DCTCP. DCTCP, Datacenter TCP, is a congestion control algorithm which is able to respond to, is able to be aware of congestion before we end up in a situation where packets are dropped. And that's a very, very powerful thing for us in these circumstances. So, and the third thing we need is we need to be able to handle the control loop. So for that, we need buffering. On the NIC chip we're using in these cases, we actually have 17 megabytes of on-chip SRAM, which is a pretty large amount, and that's what we're using to buffer these packets and be able to handle the situation. So what actually ends up happening at the end? Excuse me, I think we've lost a couple of marks at the end, but that's okay. So first up, what happens is the storage head node opens up a congestion window. So as this congestion window opens up and increases, the throughput will increase because we're using more of the pipe. Think about it as water. If your congestion window increases, you're able to send more traffic, you're able to utilize more of the link. What then happens is the buffer reaches the ECN marking threshold, because what's happening is the window is increasing and increasing and increasing. So when it gets to the point where it's not able to actually sync the traffic, we start buffering packets. And then we at some point reach the ECN marking threshold. At that point, we start setting what I've termed here the ECN flag, but it's the ECN congestion event bit in the packets heading into the NIC. Sorry, heading into the twin leg. This then leads to the returning packets being marked with an ECN echo flag. This then passes all the way back to the head node and reduces the congestion window. So immediately we've reduced the throughput without actually having to drop packets. And while this is happening, the buffering is handling the packets in flight. By putting these things together, we're able to minimize the drops and reduce the tail latency. So very quickly, one thing I just wanted to quickly touch on while we were going through this presentation is throughput. So usually a lot of the time with DCTCP implementation in the past, you've seen people worry about throughput. Now the reason for that is because they tend to set very low ECN marking thresholds because of the fact that they don't have a lot of buffering to be able to handle that control loop. Because of the amount of buffering we have available on the NIC, we're able to handle that control loop. So we're actually able to open up the congestion window to a point where we're actually able to get a very nice throughput, as we saw in this test, which is one of the initial tests we ran in the lab. I haven't got too many of the lab tests in here because we actually ended up running quite a lot actually in the data center. So what were the tests we were running in the data center? So the first thing we did was to test the viability of this as a solution by using the 25 gig PCIe NIC with its PCIe artificially limited to 12 gig. What this led us to have is a bottleneck there, as we can see. Then we also did some tests using iPerf as well. So this was just to increase the stress, so really to increase the amount of problems we would have and to increase the trouble we'd run into. And these were the results we saw. So actually at first we didn't even need the iPerf traffic to be able to show the results we wanted to show. This is some application data traffic, and this is the actual latency at P99 for the queries of that application. And as you can see, at the peaks, which are at 5:30 a.m. Pacific time and about 7 to 8:30 5:30 a.m. Pacific time and 8:30 a.m. Pacific time, which are the peaks for East Coast and West Coast. This is a West Coast data center. We would see the spikes in the non-DCTCP, non-adaptive buffer management systems, which is the orange line. And then the blue line is what we were able to do once we added in DCTCP and buffered appropriately. But as I said, we also did some iPerf tests. And the reason we did those iPerf tests was because of the fact that we wanted to see if we could break stuff. And that actually led to, I think, what is one of the most important findings we had, which was congestion control interference. So one of the problems you run into is if you are running DCTCP in our controlled system, which is the head nodes, any sort of extra traffic we add in like iPerf, and the compute nodes, then you also have other traffic from outside there, which are all the requests coming in over the system. All of that stuff is still handled by cubic traffic. So cubic is obviously only drop sensitive. And this means that if we mix these two, the cubic would just completely dominate all of the buffers because it wouldn't react until it was dropped. Now, this was a pretty pathological case which we managed to see one day, which is when a database partition lined up with one of our iPerf bursts. So you can see we have iPerf on off for 30 seconds at a time here. And then we had this latency explosion. So how do we get around this? The way we get around this is we used some of the work that Larry had done, who's here in the front row, when he was looking at this a couple of years earlier, which is by splitting the queues by congestion control. And this is what happened. So as soon as you can see, as soon as we split up the queues by congestion control type and use different thresholds and different marking levels for the different congestion controls, we were able to maintain fairness. And that was a pretty important finding. So finally, okay, we saw that this worked, and that was very encouraging. So what did we do at this point? We built a NIC. So we built a OCP 50 gig Agilio CX SmartNIC. And what we have in there is we have software which runs a very simple L2 switch. we have a, excuse me, I don't know what's happened with the lines there, my apologies. We have a simple L2 switch. We then have a classifier. That classifier in this case is based on a Linux kernel classifier called U32. So we're actually offloading Linux kernel classifiers into the NIC here. And we're using that classifier to determine the congestion control type that the traffic which is coming in is, and that steers it to the correct buffer queue, and with the different thresholds and the different marking. This is actually, at the moment, we're working on replacing this logic with offloaded BPF, which is something which is used extensively within the kernel at the moment. So that would mean that we use BPF as the classifier, and we can actually even use BPF with redirect as the L2 switch. And that means that we have something which is fully software defined and is compatible with tools which are used in kernel networking today to be able to program this. So effectively, it's similar to what Dan was talking about around white box switches. We're effectively trying to build white box NICs. And at this point, I'm going to hand over to Amal about what the testing we did with this NIC once we actually plugged it in.
All right, so similar to a couple of the lines got messed up, and some blocks are missing, but I'll just fill that in for you guys. So similar to the single host test that Nick talked about, we ran a multi-host test where the interactions between the Tioga Pass head node and below that would be the storage node, and the compute node were DCTCP, and then external traffic from the rest of the data center was cubic. So we first tried just a single slot active. So in this case, we're highlighting the incast issue because we have 50G going into the NIC and a PCIe by 4 going to the single slot, so that's 24G. So our bottleneck here would be right there at the PCIe. So the bottleneck is restricted to the NIC. And the latency results we see for the latency-sensitive application that we ran in the data center show that we were able to meet the SLA and we didn't run into significant issues despite the incast problem. So the next thing we did was to add in the rest of the 3 slots on the compute node. So now all 4 slots on the compute node are active. They're interacting with their own head node in order to access storage, which is what the head node is supposed to have under it, right? And we ran the same test again, but with all 4 slots active. And we were able to see here that all of the slots can maintain the 20 millisecond SLA firstly, and then secondly, they don't have fairness issues, which you may have seen in systems like this one, where latencies are uneven across the hosts. But in this case, they're all around the same for the duration of the 24-hour period. So the next thing we wanted to do was add additional network stress. And in this case, we go back to the single slot active case, and we add in an iPerf server. Now, in this case, the iPerf server is actually running cubic traffic. The DCTCP traffic is still between the compute node and the storage node, but iPerf is adding cubic, and we've split up the congestion control queues as Nick had talked about earlier. Here, again, the bottleneck is still at the PCIe, so our bottleneck is at the NIC level. And our SLA is pretty easily maintained at around 10 milliseconds. The pulses you see are because we're turning iPerf on and off every 30 minutes in order to be able to tell the difference between the additional network stress and without the stress. And there is really only about 1 millisecond or really minor changes in the latency. So following up to that, we add in the rest of the 3 slots on the compute node, turn them all on, and then we add, each of them has their own iPerf server serving at 50G of cubic traffic and Tioga Pass head node in order to access the storage nodes. And then, so then in this case, if you're observant, you'll notice that the issue really kind of gets pushed up to the switch because you have effectively 400G of traffic that you're channeling into a 50G NIC. And we see that pretty clearly with the latency of our applications, which is well above the 20 millisecond SLA and pretty peaky. So we found that we needed a solution for congestion in the switch as well as in the NIC. Our solution, we were still able to create situations where you can have sufficient congestion that your latency isn't guaranteed to be below the SLA. So Larry, who's sitting up here again, had run some tests on ECN, enabling ECN in the switch with DCTCP. And the application that he used uses worker racks and storage racks. And it typically uses more than 3 of each, but for the purposes of this test, grabbing 3 of each was sufficient, and he ran a typical workload across the racks. The results of his tests are shown here. Some of the numbers are not shown, so I'll explain what's going on. The first row is that the fabric switch to worker average link utilization. And in Cubic, it's 69.9, and DCTCP, it's 69.8. So link utilization is the same across both the Cubic case and the DCTCP case. And what that tells us, that's important because even though it's below 100%, you still have cases of congestion and discards because of the burstiness of the traffic patterns. The next thing to note is that the CPU utilization is actually, for storage CPUs, it's the same exact value in Cubic and DCTCP, and for worker CPU, it's 1% higher. So that tells us that DCTCP doesn't significantly increase the CPU utilization. And then final thing, this is the most important one, so I'm glad that one's showing, is that the fabric switch discards drop to 0.3% of the Cubic value when you run DCTCP and enable ECN in the switch. And there's some cross-traffic occurring between the worker racks. The discards there also drop from 407 million to 0, which is blank. And then storage retransmits and worker retransmits are also down. What's even more interesting, I think, is that if you increase the load until the link utilization is up to really close to 100%, then the benefits of using DCTCP are even more enhanced, because the number of fabric switch discards you get becomes 0.1% of the value with Cubic, and the number of retransmits you get are also reduced more significantly. So using Larry's tests as backing for our hypothesis, we moved forward and took the same exact case we had before, where we had the P99 latency peaks and congestion in the switch as our logic for what was causing that, and we enabled ECN in the switch. And at that dashed line at the 20 line mark is the SLA. So we were able to reduce the P99 latency down, and it's consistently meeting the 20 millisecond SLA in the same exact test setup. So in summary, what we found is that we can link congestion control advances and SmartNICs to reduce our tail latency significantly, which is helpful because it allows us to apply Yosemite v2 systems and flash disag to a wider variety of use cases, including latency-sensitive applications. But we found that without implementing ECN in the switch, you can still construct cases where you have significant congestion and high tail latencies. So in order to guarantee a low tail latency, you need to have ECN and DCTCP both enabled in the multi-host NIC and in the rack switch. Here's the products that we used. You can check out these links if you want more information, and then there's some mailing lists as well that you could take a look at, along with the 2 papers that we referenced. Thanks. I think we're open to questions.
Anyone? Yep. So the question is, with the larger amount of NIC buffering, do we see increased latency? And if we do, or do we only implement the buffering scheme when we detect congestion? The answer is the second one. The extra congestion only, the buffering scheme only gets enabled when we detect extra congestion. Yes. Anyone else? Okay, thank you.
Just wanted to quickly ask, in terms of the traffic that you run this against, there was iPerf.
Yep.
Are there any other applications?
Yes, so we were running an RPC-based application which is internal to the Facebook Datacenter. That was where we were getting all the sort of ODS-style graphs from and so on. So the iPerf was only spoiler traffic we were adding in to really try and break things. Most of the time, we would find that there would be specific bursts on specific systems, but iPerf was just a way of trying to completely hose the system. So it was just an extreme test case, was adding in the iPerf. The real traffic is the other traffic. This one is one for Larry, so I will hand it down to him.
So he's asking on the experiment where we had 3 racks on one side and 3 racks on the other one, whether it was a full mesh or like mostly incast. And for that experiment, it was mostly read traffic. So it was primarily incast from the storage into the workers.
Thanks, Larry. Anybody else? Yep. Yeah, the iPerf was really just extra traffic. So you meaning that we actually end up in a situation where we're sending from the multi-host NIC through to the other end, which is kind of a head node. Yeah.
So yeah, it was labeled as iPerf server. That was kind of a misnomer. It's actually iPerf client. The iPerf server was running on the Yosemite, as you're saying, but that was the server used exclusively for the purpose of iPerf. Right.
Yeah, no, and also the point is just if things were reversed, what would happen is that then you end up in the kernel buffering the packets. So you kind of get basically a mechanism inside the Linux kernel to be able to smoothly pass the packets out. So there is that on the other side as well if you need it. So the question is, were we using PFC or any other mechanism like that, or just ECN? And the answer is no. We did not use pause frames. We did not use PFC. We put nothing like that in. We simply used the Linux kernel congestion control stack, TCP stack, sorry.
So when you use an iPerf, is this just 64-bit?
So we were sending 1500 byte traffic through just to basically fill up the pipe. So that's a good question. Jumbo frames is a good one. So it shouldn't really, actually. We did some tests with jumbo frames. They work quite nicely. The problem with jumbo frames is basically your congestion mechanism gets a bit coarser because of the fact that you have fewer drops or fewer bufferings. So your congestion window goes more like this. It was just better when we were using 1500 bytes. Exactly, TCP takes care of things. That's a good question. So how are we detecting congestion? So in the NIC, we obviously have a mechanism whereby we're passing packets across PCIe. So what we're looking for there on the NIC side is we're looking for PCIe credits. If we can't get a PCIe credit, we know our PCIe is under strain. Therefore, we buffer the packets.
Any other questions? So just sort of thank you all for presenting. This was really, when we were looking at the proposals for this track, we were excited about this because it was really bringing some of the NIC technologies as a way to think about the end-to-end application performance as well as on the switch. In some of the earlier sessions today, we've been talking, people were asking about buffer depths, people were asking about end-to-end performance, and so this gives hopefully a little bit of another slice into how we can tackle those application problems in the network. So again, thank you all very much for presenting.